So, welcome to the lecture series of VLSI Design BEC 701. This is the lecture number 2 and this lecture is from unit number 4 and which is related to semiconductor memories. So, let's start with the outline of this lecture. So, basically in this lecture, we are going to see the key concept of semiconductor memory, which include the memory array organization. We will see the designing of DRAM cell and how the evolution of DRAM cell that we'll see in this lecture. Basically, this is the part of unit number 4. So, in VLSI design, in the previous lecture, we have seen the complexity of VLSI system is very high. So, in the current scenario, this is the requirement of the society that everyone want the handheld device, portable device, or we can say portable electronic gadgets. So, for these portable gadgets, the important parameter is the power consumption. We need the high battery life. And another thing is we need the high memory bandwidth. We are having so much of data in terms of image, video, audio. So, the requirement of memory is also very high. There is a fact that if we see any system, so like the circuitry consumed by the particular system is less than the area consumed by the memory for that particular system. So, you can imagine like if it is a circuit of full adder, so for like adder, like number of transistors are 8 for example, and to support that particular application we require memory size which includes like thousands of transistors. You can see the advancement in the memory. Previously we have seen in the market like 1 GB 2 GB pen drives. Now if we are looking for the pen drives, then there is no 1 GB 2 GB 3 GB 4 GB type of pen drives are available in the market. So basically the requirement of memory is increasing day by day. So it is very necessary to see how to optimize the design of memory cell. So that's why this topic is very interesting as well as very significant in reference to the VLSI design course. So memory is what? The capable storing of information or large quantity of the digital information, and we require to enhance the memory bandwidth. So that's why we are studying this topic. So semiconductor memory can be divided into two parts. One is read-only memory and second one is the read-write memory. So these are the two broad category of semiconductor memory. Here the semiconductor word mean we are designing the memory with the help of semiconductor technology like CMOS, CNFET and many more like FGMOS, floating gate MOS transistors. So there are advancement in the semiconductor technology, and the same advancement we can see in the semiconductor memory. So here the meaning of semiconductor is that we are implementing memory using the semiconductor technology. So semiconductor memories can be broadly classified in these two categories: read-only memory and random access memory, which is known as read-write memory. So read-only memory, in that case, the retrieval of previous stored data is possible, like it is known as non-volatile memory. If we store some information that retain in the memory, so it is like permanent kind of memory, whereas the random access memory are the volatile in nature. Like if power is connected to the circuit, then bit is stored. Whenever power is off, then data vanished. So these are the two broad terms like non-volatile memory and volatile memory. Further, the non-volatile memory can be classified into the mask programmed ROM, programmable ROM, erasable programmable ROM, like we can program also. Although it is known as read-only memory, like we can read one-time write operation and we can read that information indefinite time. So, but there is a option to program the ROM also. So, these are the categories: erasable programmable ROM, electrically erasable programmable ROM, and in case of random access memory, there are two broad categories: static RAM and the dynamic RAM. So, in static RAM, the data retained in the memory whenever the power is connected to the circuit, and there is a static power dissipation because all the time the power is on. In case of dynamic RAM, the concept is similar to the dynamic logic design. Like all the time there is no need to switch on the power. Here we use the capacitors and the data is stored in the form of charge in the capacitor. So the charge is stored in the capacitor and we require only refresh cycle. Like we have to refresh it periodically so that the leakage issue of the capacitor can be handled, but there is no need to permanently switch on the supply. So in static there is no need to refresh it, but in case of dynamic additionally we require some refreshing mechanism. So these are the broad classification of RAM and ROM. In that particular unit, which is unit number 4, you have to study all these memories, like the types of read-only memory and type of random access memory. And if we see the scenario in current industry standards, so we are focusing on the DRAM design because the area requirement or transistor count is less in the DRAM design. So as the requirement of storage is increasing day by day, so it is better to opt for dynamic RAM. So the main focus of designers on the designing of RAM, which is a temporary memory, and even in the RAM designing, the dynamic RAM designing are more useful, or you can say more used memory type. So here in this unit, we will see how to design static RAM, like designing a part of the circuit part of that particular static RAM as well as the dynamic RAM. Whereas in case of ROM, you are required to study the concept, how to design a mask programmed ROM, how to design programmable ROM and EPROMs, etc. So one by one in this lecture, I will show you the designing of DRAM only, but in the upcoming lectures, we will see the designing of static as well. So first of all, let's see the memory organization. So this diagram is very important. Like in any system, this is the organization of multiple cells in the memories. One cell is capable to store 1 bit. So in this diagram, you can see these are the various cells are known as memory cell, and there are multiple columns. Like if there are m bits, then 2 to power m columns are there. Similarly, if there are n bits at the row side, then there are 2 to power n rows are there, and the size of memory is given by 2 to power n multiplied by 2 to power m. So this is the memory size. And to fetch any memory location, so like this is the array, this can be represented like this. There are m columns and n rows. So there are 2 to power n multiplied by 2 to power m locations are there, addresses are there. So if suppose I want to fetch this address, like I want to write something in that particular address, so for that I need some circuitry by which I can select that particular memory location. So there are memory cells, and every memory cell has its address, and that address can be selected by using the row address decoder and column address decoder. So the these are the two decoder which are used to select a particular address in the memory. So we know the concept of decoder. Like in decoder, there are suppose n inputs, then 2 to power n outputs are there. Like 2 input are there, then the decoder is known as 2 to 4 decoder. For n equals to 2, it is 2 to 4 decoder. Similarly, 3 to 8 decoder. And same designing is there. So this is the general structure. And suppose this combination is for n equals to 2, 0, 0, then one line, first row is selected. So this is how we can select the row, and with the help of this column decoder, we can select a particular column. So this is how we can reach a particular location. So this is the typical organization of a standard memory. This is the same. Now see how we can design a ROM, that is the non-volatile memory. So this is just implementation using the transistors. So this is the transistor array. With the help of transistor array, we can write any bit in the permanent memory at particular address. So here you can see that this is the simple concept. Again, decoder is there. So the decoder part is removed from this diagram, but still you have to see that there is a decoder by which we are decoding particular row. So for example, if this is the combination 1, 0, 0, 0. So in that particular case, this row 1 is high and other rows are 0. Similarly, if column is 0, 1, 0, 1. So like 0, 1, 0, 1. So this particular column is high and this is also high and other are 0. So this is how you can fetch that particular location. And if transistor is, if logic bit is stored, the concept is similar to the CMOS inverter. So if logic 1 is stored, that represent as the absence of the transistor, and if logic 0 bit is stored, it represents the presence of active transistor. So for example, we have located these two locations, and that means there is 1 over there because the absence of transistor is there. Absence of transistor means this particular point is connected to VDD, and again this particular point is located to VDD. So here the bit is 1, whereas suppose this particular point is 1. If this is 1, in place of 0, if this is 1, like this is the combination. So in that case, this transistor is on because of this 1, and this, because of this VDD will connect to ground. So that will make that particular bit as 0. So this is how we can read 0 bit and 1 bit. So in particular ROM architecture, we can read 1 and 0. If absence of transistor is there, that means bit is 1. If transistor is present, then bit is 0. So this is how you can see this for all the combination of row and column. So this is the typical architecture or organization of ROM design. And again, this is the designing of column and row decoder. So for designing column and row decoder, we can see this table. Like if 0, 0 is given as an input to the decoder, then particular row will be selected. If 0, 1 is given, then row 2 will be selected. 1, 0 is given, then row 3, and for 1, 1, row 4 is selected. So this is the typical structure of decoder of row or column. Any decoder can be designed using this table. Now come to the important topic, which is the dynamic read-write memory or DRAM cell or DRAM circuit. So basically here the concept is to store the data as a charge in a capacitor. So presence of charge is considered as logic 1, matlab high label, and in case of absence of charge, it determines the logic 0. We know that the capacitor cannot retain the data or charge indefinite time. So because of this leakage, we require the periodic refreshing of stored data to avoid the modification in the charge. So if we design DRAM over the SRAM, there are so many advantages, because in SRAM there is a permanent requirement of supply, power supply, and if there is power supply which is on all the time, so definitely there is a static power dissipation. So we can reduce the static power dissipation in case of DRAM, because here we will periodically refresh the capacitor, but there is no need to always on the supply. So this is how we can reduce the power dissipation, as well as if we see the standard static SRAM cell, then the transistor requirement is 6. So the popular static SRAM cell is known as 6T SRAM. So that means to store a 1 bit, for 1 bit we require 6 transistors. So to store a single bit, for single bit we require 6 transistors. So this is the minimum requirement. In case of DRAM, we can even design a DRAM cell using only single transistor. So there is a reduction of 5 transistor to store a single bit. So you can see the advantage of DRAM over the SRAM. So now come to the evolution of DRAM cell. So this is the first and very popular design of DRAM cell, which is known as 4T DRAM cell. So there are 4 transistors in this circuit. This is the simplest one, where there are so if whenever we have seen the typical organization of memory, so there are some bit line, and some are known as the like row line and column line. So here column line are represented at bit line, and row line can be used to read and write operation. So in this diagram there are 2 bit lines, one is bit line C and second one is the bit line C bar. There is a word line which is connected to the let's say this is M1, M2, M3 and M4. These are the 4 transistors in the 4T DRAM cell. So word line is connected to the M1 and M2, and then these M1 and M2 are known as access transistors, through which we are accessing the memory. We are accessing these capacitors, where because here the bit is stored in the form of charge in these 2 capacitors. These capacitors are connected to the gate of M4 and gate of M3. So this can be written as CGS4 and this is known as CGS3. So these are the 2 capacitors over there. Here the bit line are also known as input line. Here we can input the data which we want to write in the memory, and this word line is used to given the control or to use the access transistors. So now let's see the operation of this particular 4T DRAM cell. Suppose I want to write 1 in this particular memory. So at this input line 1, so bit line C is 1, then C bar is 0. If this is 1, so here high value is there, VDD is there. This 1 we can get through a pre-charge transistor. This bit line is always connected to the pre-charge transistor. Here also and here also. So if this is 1, that means at the input of this pass transistor, these M1 and M2 are pass transistors. So at the input of this pass transistor, the 1 is appear. If we want to write something, then it is compulsory to make word line 1. So by using again the transistor, we have to make this word line as logic 1. So if this word line is at logic 1, then M1 and M2 pass transistor will be on, because these are the NMOS pass transistors. So suppose this is on, then this one can be passed to the output node, but we know that NMOS pass transistor, we cannot pass logic 1 because this is not so good to pass a logic 1. So at this node we will get VDD minus VT. We will get VDD minus VT, but this can be considered as a logic high level. So this capacitor will charge by VDD minus VT. So here we will get VDD minus VT over there. So this can be written in the memory because here this capacitor behaves like a memory element. So here you can see that the charge is VDD minus VT, whereas here this again this transistor is on, but bit line C bar is 0. So this capacitor is with a 0 charge. So now you can see that this one bit is right over there. And you can read also with the help of the same diagram, you can read that particular bit by seeing that which transistor is on and which transistor is off. So this is how you can store, or you can write 0 or 1 in the 4T DRAM cell. But there is no such advantage of using this 4T DRAM cell. It's better to use 6T SRAM in place of 4T DRAM because here we require the periodical refreshing also. So there is not much advantage of reducing transistor count in that particular DRAM cell. So it is required to reduce the transistor count. So in next slide you can see the structure of 3T organization of DRAM cell. So this is known as the evolution of the DRAM cell. So in that particular circuit the transistor count is less. So there are only 3 transistors are used in that particular circuit, and here only one capacitor is used. So the operation of this particular circuit we will see in the next lecture, but from this slide you can see that there are less number of transistors. So by using the 3T DRAM cell, we can also write bit 1 or 0, and we can also read by using read select. So there are two different things, read select and write select. At a time either we can select the read or we can select the write, and the bit line concept is same over there. For writing anything we require the bit line should be high. So if bit line is high, we can transmit any input through this transistor, the pass transistor, to that particular capacitor, and this is known as parasitic storage capacitor. So this is how we can implement the 3T DRAM cell. So here you can see that the transistor count is just half if we compare with the standard SRAM cell. And this is the again further evolution in the DRAM cell. This is the single transistor memory cell, which is very much popular. By using a single transistor we can store a bit. So for 1 bit we require 1 transistor, but there is a difference in this capacitor. This is the storage capacitor which is connected externally. We have seen the previous circuit where capacitors are parasitic capacitance because of the transistor. So in previous one we have seen that the capacitors are connected, you can see over there, but these are known as parasitic storage capacitors. So previous one are the system capacitors like transistor capacitors. Here we have externally connected a capacitor to the circuit. So by using this additional capacitor we can implement the DRAM cell using single transistor, and this is very much popular in the industry because of 1 transistor and 1 capacitor. It is having less transistor count, so less power dissipation, and it is also fast because speed should be very high. So these are the evolution of DRAM cell. In the upcoming lectures we will see how we can design SRAM cell too, and you are required to study the operation of 4T, 3T and 1T DRAM cell in detail. So thank you so much from my side.